Okay, so we are started. Here we go. This is our, I guess, fifth meeting. Yeah, we're in the third week. We only met once the first week. This is our second time this week. 2 times last week, 2 times this week. This is our fifth meeting. I usually sort of do 2 meetings per unit, and then somewhere along the way, one unit sort of runs long, students have lots of questions, and that works out so long as you don't try to do that with every unit. Will be okay. And it usually ends up to be just before test 1. People are looking for more answers to questions and sort of going past my 2 meeting limit, but it's just to keep us basically on track, but there is some flexibility. So when you need to take advantage of that flexibility. So, okay. So in my mind, we have finished Unit 2. There were the lectures, that those you watch on your own, but you're certainly free to ask questions about them. The homework in Unit 2 is to read Chapter 2 of the book and write me a summary of about a page. There were 3 parts of the lab. One involved resistors, and the others were about sort of truth tables and logic gates. There were 2 Zoom sessions which are posted, and then there are some things that popped up along the way that I posted. So I was, we wrote a big truth table, and I sort of wrote the Boolean expression for it, and then I built some circuits, some products and a product of sums. And that's just a single file, but I don't know how the system will handle a multi-sim file, so I sort of zipped it up for sort of protection. Okay, so I'm telling you what in my mind is done, but I'm waiting to see if there are any questions. If you've attempted any of the lab parts and you had questions. I'm going to re-answer some question I was asked. So one thing, say, for this AND gate is to pay attention to which row. So right now with these switches up, this input is high and this input is high, so that's corresponding to this last row. And I think this is an accurate measurement. So that would be 5 volts. And then there's a question of high or low. So part of high or low is determined by what is the range we're expecting. And so the battery is determining that. The battery is saying 5 is our high and 0 is our low, because we have the low end of the battery attached to ground and the high end of the battery up here. Okay, so that is our sort of range of possible voltages. Sometimes there's a different range sort of hidden from you, but it's not hidden from you in this case. The range is from 0 to 5. We're reading out here a 5. So within the range from 0 to 5, 5 is on the high end. And if you get a 0, it's on the low end. And that's sort of this right now as this type of AND gate is, I would say, idealized. You're going to get, an absolute high of 5 and the absolute low of 0. But that's not always going to be the case. So you've got to get comfortable with sort of maybe anything more than, say, if the range was 0 to 5, then anything like 3.5 or higher, if you're breaking it up into a Boolean high or low, like 3.5 or higher would be high. Low would be like, anything like 1 or below. And then there's kind of a no man's land that we hope doesn't happen. And so that's what I'm expecting here, highs and lows. Okay, anything else? No, but that was a question that came up, like, what's the meaning of, what do you mean by high and low? And it's just emphasizing that concept that we're doing a lot of binary stuff. And
have reached the offices
So the reason for asking for is it high or low is to emphasize that we're working with circuits that are supposed to be logical or binary. And so our outputs, our input should be highs or lows, our output should be highs or lows. And so we need things that are interpretable as high or low. What else was I asked? This part we effectively did together, except the ones and the zeros are different, but we effectively did this. So the connections will change, but the overall idea is there. This one usually confuses people. Here I want to show that the truth table can come from a scenario, not just me making up ones and zeros or somebody else making up ones and zeros, but from an actual something that we might want to build. And so we might want to display in decimal a number that is coming to us as binary. So 0000 is a binary number corresponding to 0, and then I would like to light up this display to display a 0. And then A, B, C, D, E, and F should all be lit, and G should not be lit. So it'd be, and I'm going to assume that lit is a 1, so it'd be 1, 1, 1, 1, 1, 1, 0. The 8 is everybody lit, so that's 1s all across. So that is the scenario. That's the 1s and the 0s. You have some number, 0 through 9. You want to display it using these 7 little lights. And we're going to give it a 1 if we want it to light up, and a 0 if we don't want it to light up. But then when it comes time to build a truth table, when we talked about, expressing truth tables, we had 1 output, and now we have 7. Well, you just do it 1 at a time. So, and all I've asked you for is segment A. So you just, once you filled out the table, then you imagine that it's just this. And you just ignore these. You're writing the A, there's an A output. It's different from all the other outputs. And you just write the expression for A. I don't say whether to do sum of products or product of sums, so you get to pick. They both work, you pick. Okay, so those were questions that have come up from students in this class and have come up with students in the past. I asked one more time if you had questions on Unit 2. All right, and I'm notoriously bad at watching chat, so you should probably just yell out online, people. All right, so let's move on to the Unit 3. There are 2 big things in Unit 3. One is combinations of resistors. So our circuits with resistors are just getting like more complicated. So things haven't changed. We still are just going to do series and parallel. It's possible that you can have some circuit with resistors that are neither in series nor in parallel. And we're not going to do that. It's always for us going to be either series or parallel. But now what we're going to do is there's going to be some series and then some parallel and then some more series and then some more parallel. And we're going to work down to sort of a single resistor. So that's what this part is about. Sort of many resistors sort of all over the place, and analyze it. Look for series, look for parallel, make your substitution, and keep going and do it until you get down to 1. And sometimes they're what I call a couple of backward steps. And then a different kind of simplification, the Karnaugh map is a Boolean expression, a truth table simplification. And so it's a way to simplify a truth table. So now my question is, which one do you want to tackle first? So again, there were lectures. I'm going to have you just watch those lectures. But in terms of me sort of demoing it in the class, Do you want to do resistors or do you want to do Karnaugh Map? Does anybody care? Nobody cares. All right. So I have Karnaugh Map first. So let's go with that. Okay. First, let me look at what you guys have to do. So here is lab 3, and it starts off with one of the same things as lab 2. Here's some truth table, and you write a sum of products and you write a product of sums. Okay, so that's just a repeat. If I repeat something from one lab to another, that means it's one of the core concepts, and that means that you should make sure you know it. This is like this, and then another one that's this is going to be on test 1. When's test 1? We're going to do 4 units, and that's going to be the material for test 1. Then we're going to do the 5th unit that's not on test 1, and then we're going to come back and do test 1. So that when we're doing unit 5, that's going to give you a chance to finish a lab and get it to me, and me to grade it and give you some feedback. But so we're expecting a test in like week 6, the way that goes. So each unit takes about 2 days, so about a week. We've got 4 units that are on the test, sort of 1 unit that's not on the test, and then we finally come back and do the test. So we're expecting maybe week 6 to have a test for those who like to know when the test is.
Professor?
Yes.
Sorry. Before the test, if we have any like questions when we're reviewing, can we ask you?
Yeah, I start every day. Are there questions? And
Okay.
you could ask when I'm about ready to do unit 5. If your question's on unit 1, that's perfectly fine.
Okay, thank you.
And if the day were filled with questions and I didn't start unit 5, then I'll just start unit 5 the next time.
Got it.
I don't think you should wait that long, but you can wait that long. I will go back whenever you have a question. I will try and answer it. Okay. Here is again one of these things. There are 3 inputs, A, B, and C, and then I have these outputs, D, E, and F. And in this first part, most people do it without doing a Karnaugh map. They try to simplify this circuit by just looking at the algebra. There are 3 inputs. There's enough of a pattern that's possible here. And then on the next step, it gets a little bit more complicated, and then you should use the Karnaugh map. So let's look at 1, E or F. Do you want me to do E or F? Thank you. All right.
How about F?
All right. Somebody has a voice. Okay. Somebody cares about me, then I get some feedback, or at least an answer. Okay. So I'm going to write, to start off with, I'm going to write a sum of products approach. I'm going to copy this. I'm going to copy this. Put it down a little bit closer. Where's F? Here's the F. Okay. All right. Let me try to get that on one page. All right. And I said, let me get rid of these. I just want to focus on the F. Delete entire column. Let's do that. Okay. So here's A, B, and C, the inputs, and F, the output. And I am going to take a sum of products approach. So I focus on the ones. So here's my first 1. And in the sum of products approach, we make, we're using an AND gate. We're using a product, which is an AND, and we want to make everybody a 1. And so it's A prime, B prime, C. That was our first one. Our next one is A prime, B, C prime. Yes. Do what? Zoom in. All right. How's that? Can you see it? Yes, okay. So I focused, this one was A prime, B prime, C. This next one was A prime, B, C prime. Here's a one down here. It is A, B prime, C. And then the last one is A, B, C prime. So this is the unsimplified. So this is sum of products. And it's unsimplified. Okay. Non-simplified, I don't know. It doesn't like that word. I don't care.
Question.
Yes.
Did you pick random ones, or like what was? How did you pick?
It doesn't matter. I give you the scenario and you have to live with it. So this one was not gray code, happens to be a particular thing, so it's not random. I give it to you. And if I give it to you, it doesn't matter whether it's random or not. I gave it to you and you have to live with it. So I gave you ABC were my inputs. I gave you three outputs I was interested in. Casey, I think, told me to do F. And so then I am focusing on the output of F. Okay. Is it random? No. Is it any different from if it were random? No. So it doesn't matter whether it's random or not. Okay. So I'm going to talk about what gray code is because it's important for the simplification approach. But for what we're doing right now, it doesn't matter what the scenario was. I gave you all the zeros and ones. And it's the same as if I gave you random ones as if I give you ones and apply to a scenario. It only matters if you have to fill in the scenario like you do for the lighting up the display that we talked about previously. Okay. So now, how do things simplify? Things simplify if I have now 4 terms. You see, I have 4 terms here. If I have 2 terms that are different by only one of the inputs. So these two differ by 2 things. The A prime is the same, but the B is a prime here and B there, and the C is a C here and a C prime there. So that is not a simplification. Simplification is when there's only one thing different. So these first 2 terms do not lead to a simplification. Then I look at I look for a different pair. Let me look at the first one and the third one. And it is the A changes. One was prime, one's not. The B's are the same. They're both B prime, and the C's are the same. So the first and the third will simplify. So the first and the third will be A prime, B prime, C plus A, B prime, C. I factor out the changing thing. The B prime and the C were common, so I factor out the common stuff, B prime and C, and I have the following. So the B prime C were common, and the A prime plus A, and that plus is an OR. So A is something that's either true or false. So let's assume that A was true. Then A prime is false, but A is true. And this is false or true, and that would be true. If A were false, then A prime would be true, and it would be true or false, and that would still be true. So this says either way with A, whatever A is, whether A is true or false, this combination is true. And so I can get rid of it. That's the simplification. That's where the simplification comes from. So let me do this. So I get rid of, see if I can make this a little bit wider. There we go. That's where simplification comes from. If you differ by one and only one term, that gives you a simplification. I was looking for that with the first and the second term, and it didn't work out. But the first and the third term did work out. Now, if life is easy, the second and the fourth, and in this case, life does happen to be easy. So we're doing now the second and the fourth. Okay. And so what was that? That was this guy. And the last guy. And they differ. It's B, C prime is common, and the A, no, what did I do? This, I wrote this down wrong and you didn't yell at me. I always yell at you when I make a mistake. This guy was A prime, B prime, C. This guy was A prime, B, C prime. This guy was A, B prime, C. This guy was A, B, C prime. Okay, A, B, C prime. Now I got it right. Oops. So again, the A factors out. So it's A prime plus A, and then it's B, C prime, which is just B, C prime. So my first and third term simplified to B prime C. My second and fourth term simplified to B, C prime. So far, you don't have to be so wordy when you do it, but so far it's B prime C plus B, C prime. And then we ask, does it simplify any more? And the answer is no. There is, the B changes, it's a prime here and not there. You know, here's a B prime and here's just a B, and here's a C and there's a C prime. It does not simplify any more than that. That's as simplified as it gets. Now there's a way to fake it to build a circuit, because this combination occurs a lot. It's not a real simplification, but just because it's something that happens a lot, they make a gate that that does this, and that's an excluded OR. So this happens to be a B excluded OR with a C. Again, it's not a genuine simplification. Here was a genuine simplification. We got rid of A entirely. We don't care at all about A. To know that we don't care about something is a real simplification. We don't even need A. But this is just like sweeping it under the rug. make, sort of hiding the complexity, not really simplifying it. Okay, so this is the algebra approach. You write down the full sum of products approach, and then you start looking for simplifications. And simplifications occur when between two terms, only one of them changes. A lot of people want to look here between the first and the second, and they want to factor out a prime. That doesn't help on this. It's not a simplification. All right. Any questions? All right. So now I want to start looking at this thing called a Karnaugh map. The first thing about a Karnaugh map is you write the truth table in a different way. So A, B, C, D are the inputs, and here are the outputs. Is this some scenario? Is this just random made up shit? It doesn't matter. It's given to you. You have to live with it. It is what it is. Can I think of some scenario with these numbers? Probably not. But you just have to deal with the numbers I have here. Okay. Now what I'm claiming is I can arrange the inputs in a different way. I have A and B inputs running down the rows. I have the C and D inputs running across the columns. I need all the combinations. The combinations of A, B are 0, 0, 0, 1, 1, 1, and 1, 0. That's all the combinations of A and B. All the combinations of C and D are 0, 0, 0, 1, 1, 1, and 1, 0. That's all the combinations of C and D. And then I can get all the combinations of A, B, C, and D together by using this grid. So here's some combination of A, B with this combination of C, D, and that would correspond to this cell. Whatever, it's like Excel and the numbers and the letters, or if you've ever played Battleship, it's, you specify a row and a column, and you've specified an output. All right. So now I want to convince you that all of the outputs are there. Here, we've talked about this in the past. Here, all the inputs, are in a binary counting order. So here's 0, 1, 2, 3, 4, 5. So let me insert a column over here to the, what is that, left? And this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, or I could use A, B, C, D, E, F. Okay. Now, I'm going to first I'm going to, before I worry about the outputs, I'm going to worry about, do I have all the inputs? So I'm going to put in here at first, not an output. That's what I eventually want to do. I want to put an output eventually. But for now, I'm going to put in the number of the inputs to just see if they're all there. These, I know they're all here. There are 16 of them. I start at 0, count up to 15. Those are the binary numbers. All the binary numbers are different from one another. So I know I have all the combinations. Do I have all the combinations here? Well, here's 0, 0, 0, 0. That corresponds to 0. So let me make these, I don't like dark red, okay. Here's 0, 0, 0, 1. That corresponds to 1. 0, 0, 1, 1. That corresponds to 3. And 0, 0, 1, 0. That corresponds to 2. I pause. I wait for you to say, I have no idea what you're doing. Everybody knows what I'm doing. Oh, yeah. See if I can't make this bigger too. I don't need that one yet. I'll try to make it bigger. That's too big to fit on the same screen, I think. What font size works? 16. All right. All right. So I said this square here corresponds to A is 0, B is 0, C is 0, D is 0. That corresponds to 1. Sorry, that corresponds to 0. This cell corresponds to A is 0, B is 0, C is 0, D is 1. That corresponds to number 1. This guy corresponds to A is 0, B is 0, C is 1, D is 1, and that corresponds to 3. Then this one corresponds to A is 0, B is 0, C is 1, D is 0. That corresponds to 2. I'm just trying to convince you they're all there. This guy is 0, 1, 0, 0. That's a 4. This guy corresponds to 0, 1, 0, 1. That's a 5. This guy corresponds to 0, 1, 1, 1. That's a 7. This guy's 0, 1, 1, 0. That's a 6. This guy corresponds to, here's 1, 1, 0, 0. That's an 8 and a 4. So that's 12. Here's a 1, 1, 0, 1. That's a 13. 1, 1, 1, 1 is 15. 1, 1, 1, 0 is 14. Is that right? It's 8 and 4 is 12 and another 2 is 14 and no ones. 1, 0, 0, 0 is 8. 1, 0, 0, 0 is 9. 1, 0, 1, 1 is 11. And 1, 0, 1, 0 is 10. So everybody is here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Everybody's here. So all I'm doing is rearranging the inputs. All the inputs were here in binary counting order. All the inputs are here in this crazy thing. So do you believe that? Okay. Now I'm going to copy this down and do it again. But I'm going to use the outputs this time. Instead of putting the numbers down here, instead of using this column and filling it in, I'm going to use this column and fill it in. All right, so I'm going to take these all out. Okay. Now I'm going to use this column to fill in these. because that's what really belongs here is outputs. Okay. Let me show you this pattern here. It is, here's the order. You start and it's 0, 1, and then you skip to the last column and then you come back. So it's 1, 2, sorry, 0, 1, 2, 3, 4, 5, skip and come back, 6, 7. The rows do the same thing the columns do. So when you get to the, the third time, you skip and then you come back. So when I was dealing with columns, it was 0, 1, and I skipped and I came back. And then I did the second row, and now my third row, or the third time I'm doing it, I skip to the last row. So 8, 9, skip to the last 10, 11, and then 12, 13, 14, 15. So I'm going to come down and fill in these 1s and 0s following that pattern. So the first, this was a 1. Here's a 0. This next guy is a 1 that goes here. And this next guy is a 1 that goes there. So let me make that some color, orange, and make these orange. So those first 4 filled in here, and it was, here, here, skip to the end and come back. Okay, the next 4 are all 1s. And they go here, and it's 1, 1, skip, and come back. Is that okay? What do I want for this one? Nice blue. This is the third time I'm doing it, so I skip down here, and I fill in 0, 0, I skip, and I come back. And then this last guy, I'll make, I don't know, purple. And it is 0, 1, skip, and come back. I don't want to do your lab for you, which I've been doing, so that was bad on me. I'm going to change the numbers and we're going to do it again. Because the step 1 of the Karnaugh map is to get it from the 1 order into the order we need for a Karnaugh map. So I'm going to copy this crazy thing down and change the numbers. So I'm not doing your lab. Cover page. I don't want to cover page. I want page break. I want a page break. There we go. So let me paste this in again. There we go. Now what I want to do is change this data and do it again. Okay. So I need 0s and 1s. Let me just play some calculator game. There's a calculator. I'm going to go in what? Scientific. I'll start with E, and I'll take 1 on E. Why? I don't know. I don't care. And I'm going to multiply that by 2 raised to the 16th. And this is just a way for me to get random numbers. Okay, so here is some number. This is not something you have to know. This is just me making up numbers. I'm going to go over to programmer mode. I'm going to paste the number in there, Control V. And here's my 16 numbers that I'm just going to fill in here. So 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1. Just some way, doesn't matter. It's some way for me to make up a truth table for us to analyze. It might as well be random. Doesn't matter. I'm giving this to you and you have to work with it. So it doesn't matter where it came from. You have to analyze it. Okay. First step of the Karnaugh map is to move from this style of truth table, this binary ordered truth table, into this standard truth table that we use for the Karnaugh map. So here I am in this, I don't know, yellowy, orangey area, and it is 0, then 1, and then I skip to the end, so that's a 0, and then I come back, that's a 1. Are you okay? I got a nod, I'll go with my nod until somebody yells, not okay. I'm now in the green, it is 1, 1, skip, and come back. Okay, now I'm now I'm skipping, and so I'm coming down here to the blue, and it is 0, 0, skip, and come back. And then I end in the purple, and it is 1 and 1 and skip and come back. Are we following? We're following. Are we following? Okay. So that is step 1. Now, why the hell did we do this crazy crap? Why did I had it in a nice order, and then I went and changed the order, and why would I do that? Let's look at this A, B going down here. From row 1 to row 2, 1 bit changed. Only the B bit changed. When I go from row 2 to row 3, only the A bit changed. When I go from here to here, only 1 bit changed, the B bit. Same thing when I'm going across. Only one from this column to that column, only 1 bit changed. When I go from this column to that column, only 1 changed. When I go from this column to this column, only 1 bit changed. This is known as the gray code order. It's an ordering of bits where from one arrangement to the next, only 1 bit changes. Okay. So I have all the combinations. Not only do I have all the combinations, but I have them in this gray code order, this order in which only 1 bit changes. When we played the algebra approach to say where do we get simplifications, simplifications came from when 2 things differed by only 1 input. Remember that? Way up here, blah, 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 blah. The simplification occurred when I had 2 terms that were different by only 1 thing. The B prime, the C were common, and only A changed. That's where simplification comes from in Booleans. So here I have 2 1s next to each other. The inputs for those 2 1s have an A that changes. That means I'm going to get a simplification. So if you put your truth table into the Karnaugh Maps style truth table and you see two ones next to each other, that means there's going to be simplification. It's a way to put simplifications visually together so we can spot them without doing lots of algebra. Okay. So now we need to do the simplification rules for Karnaugh Maps. So we look for blocks of ones. Sometimes I call them groups, sometimes I call them blocks. I'll call it, today I seem to be saying blocks. Blocks of ones that are rectangular. Can't spell it all. Rectangular. Okay. So they're all ones. I said it's a block of ones, so it's going to be all ones. They have to be rectangular, no L shapes, no U shapes. They have to be rectangular. And they should be of a size that's a power of 2. We know the powers of 2, I hope. 1, 2, 4, 8. Okay. So that's what we're looking for, these blocks. The blocks should be, and then what else are we going to do? Every one of the output must be in a block, even if it's by itself. And blocks can overlap. So A1 can be in more than one block. Okay. I don't know. I don't like this red. I don't know. It's hard for me to see. Make it white. Is that visible? Not really. Go to black and then change the purple to maybe a lighter color, a lavender or something. Okay. So I'm looking for blocks, all ones, rectangles, of size 1, 2, 4, or 8. We need to account for all the ones before we're done. They might be by themselves. What else? Well, let's start there, and then I'll tell you things as they come up, and maybe if you see them coming up, you'll say, okay, yeah, I can see that. So I want you to identify for me, whether you're playing the home game or whether you're playing here in the studio, tell me a block of ones that you identify. The bigger the block, the better, the more the simplification. Do you see any blocks of ones in our outputs? Let me say here, output ones. You can tell me like the middle rows and the first columns and blah and things like that. Can you identify some blocks?
The third row.
The third row. And the whole row? Not the whole row, because it's got a 0 in it, but this was a possibility. It's got to also, so I can't do the whole row because of the 0. Then I have 3 ones in a row, and I need powers of 2, so I could do, say, these 2. That would work. These 2 would work, but actually I can do better. So what do you want me to do? Do you want me to do the first two, or do you want me to do the second two?
The first two.
The first two, okay. So in the first two, I'm going to say, that's not good enough for me, because we always want our blocks to be as big as possible. And I can make a bigger block of ones than just the third row, the first and second column. So what should it be? How can I make a bigger block of ones than just
Including the second row?
including the second row? So if I have now these four, the middle two rows in the first two columns, that's a block of 4 ones. 4 is bigger than 2, so it's bigger, but it's a power of 2, so it's okay. It's a square, which is a special case of a rectangle. So it's all ones, it's rectangular in shape, it's of a power of 2. Now the question I always ask, can I do better? So we started with a pair and we went up to a quartet, that's better. Can we go to the next, which would be 8? If we try to go for the whole first two columns, no, we've got zeros, that's no good. And if we try to go for the full 2 rows, we have some zeros, that's no good. So this is going to be sort of as good as it gets. And so let's sort of make some identification. I don't need this top anymore. I'm going to scroll down. This was to get here. I am here. I'm going to scroll down, maybe even more. Okay. And I just have this now. And my first group is, I'm going to call it the middle 2 rows and the first 2 columns. That's just for me to sort of somehow identify the group in my mind. It was a block of ones, it's rectangular, it's of size of a power of 2. And so now, okay. Once we identify the block of ones, and the ones are outputs, we take our attention back to the inputs that make up this block. So it's the middle 2 rows and the first 2 columns. Okay. In the middle 2 rows, what's happening to our inputs? A is changing. The thing that changes goes away. That's what we saw in the very beginning. The A was the thing that changed and it went away. So the A is going to go away, the B is going to stay. The input B is a 1. So we're going to have B, if it were zeros, we'd have to prime it, but it's B, the input was a 1. So far we have a B. The A, we're focusing on what made up our group, the middle 2 rows, the first 2 columns. So first we do the rows. Of the first rows, A changed, we throw it away. B stayed the same, so we keep it, and it was a 1. So we don't need to prime it, we just keep it as it is. This group is also defined by the first 2 columns. Get out of my way. Okay, here are the first 2 columns. In the first 2 columns, the input C stayed the same. It stayed 0. The input D changed. When something changes in this game, we throw it away. So we're going to throw away the D, and we're going to keep the C. But the C input was a 0, so we prime it. And so that's an expression for this group. Identify the group within the outputs, then take your attention back to the inputs. What were the inputs that led to this block? What changed? Throw it away. Any input that changed, you throw away. Any input that stays the same, you keep. If it's a 1, it's sort of a sum of products idea. If it's a 1, you keep it as it is. If it's a 0, you prime it. So the B was a 1, so we kept it. The B stayed the same, so we kept it, and it was a 1, so it's B. The C stayed the same, so we kept it, but it was a 0, so we primed it. A changed, we threw it away. D changed, we threw it away. And so I'm going to put a little X here, that just says that we dealt with them. We can use those ones again. Groups are allowed to overlap. Blocks are allowed to overlap. I told you I go back and forth between groups and blocks. So that can, I can use them again if I want, but I don't have to do anything more with them because I've dealt with them. But there are 1, 2, 3, 4, 5 ones that I haven't dealt with yet. So we're not done. So do you see any more blocks for me to deal with?
The top two middle.
The top 2 in the middle. Okay, that's good. We always ask, can we do more? I can't go down to another row because of the 0. I can't go across because of another 0. And there's also a funny thing I haven't told you about yet that I'm going to call wrapping, that the first row can be thought of as next to the last row, because 0, 0 and 1, 0 are different by only 1 bit. So if these 2 down here happen to be 1s, I could make a group of these 2 1s and these 2 1s, but those are 0, so I can't. But so the group identified was the middle 2 rows, the middle 2 columns. I always ask, can I do better? And I tried to go down a row, I was blocked. I tried to go across more columns, I was blocked by the 0s. I tried to wrap, I was blocked. I was blocked, so this is as good as it gets. And so what was it? First row, middle 2 columns. Okay. And now we need to find the expression. So here I am in the first row, and I'm only in the first row. Does the input A change? No, A changes from different rows, but I'm always in the same row, so it can't change. So I have to keep it. It doesn't change, I have to keep it. It was a 0, so I prime it. Again, I'm in the first row, and the question is, does B change? B changes as I change rows, but I'm not changing rows, so it can't change, so I can't throw it away. I have to keep it. It was a 0, so I have to prime it. Now I turn my attention to columns. I'm in the 2 columns, the 2 middle columns, and we ask ourselves, what does C do? C changes. C went from 0 to 1. The thing that changes is what we throw away. That's our simplification. So we throw C away. D, we keep. D does not change. It's a 1 in both of the middle columns, so we must keep it. It's 1, so we don't prime it. And so now that got us 2 more of the ones dealt with. I still have 1, 2, 3 ones I have to deal with. So I need some more block identifications. Do you see any more blocks? You can have a guy by himself. He could be a block if that's what we need to do, but everybody has to be taken care of.
First column, second row, and fourth column, second row.
Say it again first.
First column, second row, and fourth column, second row, because it wraps.
That's right, that wraps. So this green guy over here is somebody we have to take care of. And he's got 0 sort of all around him, unless you look at the wrapping property. So it's the second row, the first and last column. Very good. That's usually hard to see when you're starting. But, so second row, first and last column. Okay, so what's that going to be? That's this guy and this guy. It's the second row. A changes, the input A, once we identify the group, we go back to focusing our attention on the inputs. A changes from row to row, but we're only in one row, so A couldn't possibly change. So we need to keep it, and it was a 0, so we prime it. We're in the second row. B changes from rows to rows, but we're not changing rows, so B couldn't possibly change. And it's a 1, so we need to keep it, and we don't prime it. Now we look at columns. So we're in the first and last column. C change. C in the first column is 0, and the last column is 1. C changes. The thing that changes is what we throw away. And then we're going to go to the D. And here's the first column and the last column. D was a 0 both times, so it stays the same. So we're going to keep it. It's a 0, so we prime it. And we dealt with him. You have 2 more that you have to deal with before you're allowed to leave. So do we see any blocks? Do you see any more blocks? And if we need to, we'll have a block that's by itself. The bottom, this guy? Okay, so let's deal with this guy in the corner. We ask, can we do better? So we go horizontally to the, what is that, the left? And the answer was no, that's a 0. Can we wrap? No, that's a 0. Can we go above? No, that's a 0. Can we wrap? No, that's a 0. This guy's a loner. This guy is what am I going to call him? Last row, last column. He's got to be dealt with, but he has no partners. Nobody wants to team up with him. I'm not changing rows. I'm not changing columns. None of my inputs could possibly change. I just have to know what they are. So A was a 1. B was a 0, so B prime. C was a 1. So that's a C. D was a 0. D prime. There's a pattern here. When we had 4, we got rid of 2 things. When we had a pair, we got rid of 1 thing. When we have a single guy, nothing's gotten rid of. One more guy to deal with. One more guy to deal with.
Third row, middle columns.
Middle columns, that's right.
Middle 2.
You're allowed to overlap. So you're going to have to put these 2 together. This guy was already taken care of, but he makes this guy a bigger group, and groups can overlap. Can we do any better? If you go vertically, no. If you vertically up, no. If you go vertically down, no. If you go sort of horizontal, no. So there it is. That's as good as it gets. So it's, what am I going to call that? A third row, middle columns. That's these 2 guys. And that's a pair. And with a pair, we expect one thing to go away and everybody else to, so I'm in a single row. So A, it stays, and it's a 1, so it's an A. We're in a single row, B doesn't change, so it's B. No, it's a 1, so no prime. We're in the middle 2 columns. C changes. It was a 0 in column 2. It becomes a 1 in column 3. It changed. We throw it away. That's the simplification. And then D in the middle 2 columns was 1s. And so we need to keep it. It stayed the same. And it was a 1, so we just keep it unprimed. And then that's our expression. So we just put these guys together. B, C prime plus A prime, B prime, D plus A prime B D prime plus A B prime C D prime plus A B D. That's our simplified expression for this truth table. Now, if you want to go and do that the algebra way, be my guest. This Karnaugh Map stuff like looks hard, but compared to doing the algebra, trying to look through 16 terms and seeing who you can pair with, this is actually easier. But now what students often want to ask me is like, now do I come down here and try to simplify? And the answer is, if you've done this correctly, no. If you've made the groups as big as you could possibly make, there's no more simplification. Now people want to look for it here, but A stayed the same, but B changed and D changed, so that there's no simplification there. And if you've done this right, identified as big a groups as possible, there is no more simplification. If you see that there's some obviously simplification, then you either missed a group or you wrote the wrong expression. Any questions? That is hard the first time you see it. If your brain is spinning a little bit, that's okay. If you ask, I will answer your questions. If you ask, we will go through another example. And there's one more trick in this game that we haven't played in this example. And that is that sometimes this with 4 inputs, there are 16 possibilities. Sometimes you don't care about all the possibilities and you get to pick. And you have to pick to give as much simplification as possible. So even if you understand this perfectly, there's one more twist in the tale that we have to experience. Okay. So I'm not going to do anything more in, what, 6 minutes, unless there are questions of, can you say that again or do that again? Are there any such questions? Or anything else that would be fast in 5 minutes?
So you just did the sum of products.
Correct. Yeah, so this Karnaugh, but it's simplified. Like if I say I just want the sum of products, then you just give me the straight out, here are the ones, here's the expression for those ones, and you just leave it. So when I ask a question, like here, 3A, give me the sum of products, I don't want you to do any simplifying. Just this one is A prime, B prime, C prime. I don't care if there's any simplification. I don't want simplification here. But when I do a Karnaugh map, I do want a simplification. But yes, the answer that we get is in the sort of basic idea of a sum of products. We have products, and then there's sums of them. If, when we have a, the other way around, the product of sums approach, that is like not as nice looking algebraically, because you have these big parentheses, and then what you want to, your mind wants to distribute the parentheses, and it gets to be pretty ugly looking. So just, I guess, the way our minds work, our algebra works, we tend to focus on the simplifying the sum of products approach. Any other question? So what will I give you? Same thing as on the lab. I'll put this on a test, and the first thing I'll have you do is map from the binary counting order to the gray code order. That will be worth some points. Then, pardon me, I'll have you simplify, and that will be worth points. And you may have this other twist of what we call the don't care values. All right, anything before I stop recording? I'm gonna stop recording. Online people don't run away. I need to retake attendance. Nobody run away. Okay. Stop recording.